Okay, so now we're going to discuss problem 3 of the tutorial 6, and please refer to the other videos for problem 1 and problem 2. And in problem 3, we're given a system in the form of a block diagram, and the block diagram basically consists of the plant or the system 1 over s multiplied by s plus 2, and then we also have a controller k of s, and then everything is given a negative unity feedback. So we have an input R and output C. And in addition to the reference input, we also have a disturbance that enters the system after the controller over here. So there are three different sub-questions that we have to address for this problem. First of all is find K such that for a reference input of a unit RAM, we get steady state error equals 2.1. And the question specifically mentions that K is actually proportional. And the second part is that find the form of K such that given a reference input of a unit ramp, we have steady state error equals to 0. So basically here we have to find whether K is a proportional, integral, or differential controller. And then the last part, find form of K such that for a disturbance input of a unit step, we get steady state error equals to 0. Or in other words, the steady state output with respect to the disturbance is 0. So let's solve for the first part. In the first part, we know that the steady state error equals 2.1. And if we're faced with problems like this involving steady state error, we can solve this kind of problems with two methods. First of all is using the traditional method by the definition of error, which is the input minus output. And we can also solve for the steady state error using system type and static error gain table. And it really depends on your personal preferences. For myself, I actually prefer to use the traditional method because if that's the case, I don't have to memorize for any formulas at all, and it's also more intuitive. So I'll solve this problem using the first method or the traditional method first, and following with the system type and static error gain method later. So using the traditional method, we have the error equals to the input minus the output. And of course, we can divide both sides of the equation with the input R of S. And this actually gives us 1 minus CS over RS. So CS over RS here is actually the closed loop transfer function, which we can solve by looking at the block diagram. So let me solve for the rest of the problems over here. We have CS over RS is the forward loop transfer function over 1 plus open loop transfer function. And this is equal to K over S squared plus 2S plus K. And then solving for the error transfer function, we have 1 minus k over s squared plus 2s plus k. And this is equals to s squared plus 2s over s squared plus 2s plus k. And so we have error equals 2 s squared plus 2s over s squared plus 2s plus k multiplied by the input. And in this case, our input is the unit ramp. So to find the steady state error, we can do this using final value theorem, one of the most favorite formula for the class. And this is equals to limit of SES as s tends to 0. So just substitute E of s from this equation into the final value theorem, and we will have s squared plus 2s over s squared plus 2s plus k multiplied by r of s, in which it's 1 over s squared in this case. And then solving the limit, we will have steady state error equals to 2 over k. And we know that the steady state error has to be 0.1, which is given by the problem. So k is basically 2 over 0.1, which equals to 20. So in order for us to have a steady state error of 0.1 with a reference input of a unit RAM, we need to have k equals to 20. So let's solve this using the second method. We know that our system is basically g of s equals to the for loop transfer function k over s multiplied by s plus 2. And we know that this is a type 1 system because we have one integrator in the for loop transfer function. And then we also have a unit ramp input. So for a type 1 system given a unit ramp input, the steady state error is given by 1 over kV. And kV here is basically the static velocity error constant, which is given by limit of s gs as s tends to 0. So plug in g of s, which is this term, into the limit, we can get kV equals to k over 2. And of course, if we plug in kV into the steady state error, which I will continue in the new piece of paper, I can get steady state error equals to 1 over kV equals to 1 over k over 2, so it's 2 over k. So similarly, we get k equals to 2 divided by 0.1, which is 20. So these two methods lead to the same result, and it really depends on which method you prefer more than the other. So the second part of the question is asking the form of k such that for a reference input of a unit disturbance, a reference input of a unit ramp, we get steady state error 0. So similarly, we can solve this problem using both the traditional and the express method, I would say. So I'll start with the traditional method. The steady state error is given as 0, and we know that the steady state error is equals to 2 over k from the previous calculation that we get. So if we put everything in the context of a limit, so limit of 2 over k equals to 0, we need to have s at the top over here so that when we multiply 2 and s, we get 0. So in order for us to have s at the numerator, k has to be the form of an integrator. So if we have an integrator we will get a zero steady state error for a unit RAM input. And solving this using the express method, we know that the system is a type 1, and then we have a unit RAM input, and also zero steady state error. And then the requirement for a unit RAM input producing zero steady state error is that the system has to be type 2. So our system now is type 1, which is k over s multiplied by s plus 2. And in order for us to have a type 2 system, we need to have another integrator right here. So k has to be an integrator. So that is how we can make the steady state error for a unit RAM input equals to 0. And finally, let's move on to the last part of the question. It's asking the form of k such that for a disturbance input of a unit step, we get the steady state value from disturbance equals to 0. In other words, we want k such that the disturbance has no effect on the system output at all, which is what we want. We want something, or we want a controller that eliminates the effect of the disturbance on the final steady state response. So first of all, we need to note that we cannot solve this using the express method, because for express method we need to deal with system type, and when we're talking about system type, this is always the open loop or the forward loop and not the closed loop. So this is very important, and we are not able to find the open loop or the forward loop transfer function because it's actually based on the unit disturbance input instead of the reference input. So we have to solve this part of the problem traditionally. And we can find the closed loop transfer function from the disturbance input to the output, which is equals to S 1 over S multiplied by S plus 2 over 1 plus K over S multiplied by S plus 2. So this is the forward loop transfer function, and at the bottom here we have the open loop transfer function. And simplifying this term, we can get 1 over S squared plus 2S plus K. And then we can find C of S by bringing the disturbance input into the right-hand side. And of course, the steady state value can be found using final value theorem, which is equals to limit of S CS as S tends to 0. So we can plug in all the values into this equation, and the disturbance input is 1 over S, which is a unit step disturbance. And solving the limit, we will get CSS equals to 1 over K and in order for us to have CSS equals to 0, which is what we want that the disturbance output, the system output corresponding to the disturbance equals to 0, we need to have S term at the numerator so that we get a 0 over here. So KS has to be an integrator as well. So basically that is problem 3 of tutorial 6.